ma'am.
Yeah.
Start பண்ணலாம் ma'am. You can start ma'am.
Uma Mehshan madam.
No, sir.
We'll start, madam. Sumitra madam, shall we start?
Okay, sir. Okay, sir. Happy evening to one and all present here. I welcome all for the second day FDP. I hope yesterday's faculty development program was enlightening for everyone. We shall have a wonderful day today as well. Today, we are having two sessions. The first one is quantum hardware, understanding qubits and quantum gates by Dr. Smithna. The second one is quantum ubiquity, harness quantum computing for a seamless digital future by Dr. D.H. Manjaya. Now, the first session is quantum hardware, understanding qubits and quantum gates by Dr. Smith. Now, I welcome ma'am and introduce ma'am. So, Dr. Sumitra ma'am. Dr. Sumitra has completed her PhD in computer science under the guidance of Dr. D.S. Guru from the University of Mysore in the year 2022. Also, she completed her UG and PG in computer science from the University of Mysore. She cleared the GATE exam for the years 2015 and 2020. She published 9 research papers in conferences and journals, which have approximately 2 plus citations across the globe as of now. Research areas are medical image analysis and face recognition system. She is also a member of Board of Studies Committee in University of Mysore or UG. She reviewed a few research articles. Currently, she is working as a data scientist in the Department of Finance, Titan Corporate India, Group of Tata Bangalore. She is the ex-employee of Contric Private India Limited for 4+ years, and it is a US-based company. For her excellence, she has received the Best Employee Award. Her specialized areas of machine learning and deep learning, and she has good hands-on experience in computer vision and natural language processing. As a person, she is quite optimistic and always try to bring the best out of her ability. She loves traveling also. Now, I invite Dr. Sumitra for this second day FDP. Welcome, ma'am.
Yeah, thank you so much, ma'am. Am I audible?
I hand up the question to Dr. Sumitra.
You are audible, ma'am. You are audible. You can go ahead.
Yeah, thanks for the brief introduction of myself. So, I'm sharing my screen. Madam, is it fine?
Yeah, yes, ma'am. You can share.
Okay.
I am sharing my screen. Do let me know once my screen is visible.
Your screen is not visible, madam.
Yeah. Just let me know.
Yeah.
Is my screen visible?
Now you can put slideshow. I put it, madam.
Yes. Sure, sir.
Let's start with the slideshow. Yeah.
Is it fine now?
Yeah, it's okay.
Yeah. Thank you for the brief introduction of mine. As madam introduced me, I am working in Titan. Okay. Today, I am here to present on quantum computing, majorly on with qubits, means quantum bytes and quantum gates related to hardware. Okay. So, Okay, so these are the contents which I'm going to cover in this session. One is on quantum physics. See, quantum physics and classical physics, the word quantums come from the basics physics. So today I'm just explaining the deep understanding of what is a classical physics and how the quantum physics is differ from this. And I'm also explaining quantum computing, quantum bytes, or called as qubits, gates, circuit, and hardware. Okay, so these are the content that I'm going to cover in the session. So who am I? I am Professor or Dr. Sumitra. I'm a senior data scientist in Titan, and I'm also an ex-employee of Concentrix, that's Private India Limited. I'm a senior scholar, University of Mysore. I'm also a member of the US committee. I'm also a peer review committee member. Background of my education, I did my PhD in computer science, especially in artificial intelligence. My core area is face recognition system, and it's part of biometric system. I did my master's in computer application, and I'm a gay score holder. So as madam explained, this is a brief introduction of myself. I quickly jump onto the topic. So today I'm explaining quantum computing. So hardware, or how the logic of this quantum come from. Before understanding that, what is a quantum? I want the session to be interactive. It's not just it's like not like a teaching. You are all a faculty, so I want a interactive session. Hope my point is clear. Am I audible?
Yes, ma'am.
Yes. Yeah. So
Yes,
can
ma'am.
anybody say? Yeah. Can anyone say what is quantum? Not just looking my slide. Just tell me, just in one word, what is a quantum? Okay, let me explain. A quantum is a minimum amount or energy that put for any physical entity to react. For example, if we put a force in a form of energy to push one item, that is called that energy what I apply, that is called quantum. So the word quantum derived from the brain of this quantum computing is Planck's constant. Before Planck's constant come, we just understand what is an electromagnetic force. So how the electron is. See, before understanding the quantum computing, I'm just focusing on physics, especially a classical physics and quantum physics. That's why I'm bringing a brief introduction or background of quantum. So, and what is exactly the quantum means? It is a relativity theory in quantum mechanism. And before this, Planck's constants come, no? We only the Einsteins or Galileo, they invited that these are the great scientists. They brought electromagnetic spectrum or light or energy or velocity or displacement, momentum. These are all the words that brought from our big masters of like ancient Einstein, Galileo, relativity, Galileo. So they doesn't worked on this, doesn't focused on some atomic particle. See, we know that what is an atom, molecular energy. These are the things we will going to cover up. This is a like basics things from physics to mathematics, like computing. So before explaining the each technique, let me explain how the quantum mechanism works. Okay. So the basics principle of quantum mechanism is, as I said, wave particle duality. So before understanding what is a wave, what is a particle, what is a duality? See, we all know that light is traveling. Light is traveling in two directions. Light is having two property. One is a wave property, and second is particles property. Based on this wave and particle incident on any matter, that reflection comes. This is the concept behind the quantum mechanism. Next is on uncertainty principle. What is an uncertainty principle? The principle that behaves like for any situation that matters behave the same. That is called uncertainty principle. And second principle is superposition of state. What is superposition? The superposition principle makes this quantum computing more stronger. I mean, the superposition is something, it's opposite to the classical computing. Any course applied, like in a computing, in a classical computing, we have a bytes, 0 or 1. See, we have understood the logic gates, how the logic gate works. It works like 0 or 1. But vice versa, this is superposition. So in any instances, both 0 and 1 or both of them appears. So that is a power of superposition of state. So that is a third principle of quantum computing, superposition. And also we know that entitlement means when I have a energy or a mass or a force, the whatever the changes happen in one state, it is happen the same or the whatever the changes are made in original state, it is also the same in the another state. That is what, for example, if I have two planets like Earth and another planet like a Mars, they both are very far away. Even though the distance is very far, the momentum or whatever the energy that I change in one state or one planet, it is also changed in other planet. That is called entitlement. Okay, these are the principles of quantum mechanism. Moving forward, we will understand what are the application of quantum mechanism, and also we see what are the challenges involved in quantum mechanism. Okay, hope the concept is clear. Any doubt? As I explained, quantum is a discrete quantity of energy which is proportional in magnitude to the frequency of the radiation it is present. See, here I brought an incident light. See, light have two properties. One, wave. This is what it is moving. So this is the wave. Along with the wave, we have a particles, wave matter and particle. So these are the two properties. These are two features that light is carrying. The metal, this is the one of the matter. Matter is any object that can hold or any force, that is called matter. So if I apply any metal surface, that light going to reflect or absorb or eject, that property is called photoelectron. The major concept of this quantum mechanism is electromagnetic. So we have quantum mechanism, quantum physics and classical physics. These are two different study of physical world. With quantum physics, we will focus on fundamental property of matter and energy, what I am discussing now. And what is classical physics? Classical physics behavior only on the ordinary object, whatever the data we see, molecules or atoms, that we call ordinary object. So today we will focus on electromagnetic spectrum. So what is this? Let me hide this. This is simply popping up. Okay. Hope my screen is visible. Okay. See, I have demonstrated here electromagnetic spectrum. See, as I said, we have a wavelength. Energy, light is traveling with the particle and wavelength. It is traveling from this end to this end. See, it is stretching. It is moving with a very slight manner to the large space. It means the wavelength is distributed in such a manner from the gamma ray till the radio wave. We know that there are different radiations across the globe. One is the gamma ray, X-ray, ultraviolet ray. One is the visible ray, and next is the infrared and radio waves. We generally, there is in our home appliances, we have a microwave. That is acceptable. See, if you observe that in microwave, there is when the heat up, we will see very blue color light will sparkle. That is very minute of rays passing to the object. That is why it is blue color. For example, any pregnant ladies, they won't allow to enter to X-ray. Why? That X-ray having very high energy that will pass to our blood, and it will not entertain for the pregnant ladies, like that. So light having different wave in nature, from large wavelength to small wavelength. Here the 0.001 nanometer to 100 nanometer. So this is how the electromagnetic spectrum has splitted in different ways. We have visible light like RGB color spectrum, like ultraviolet ray, light ray, and infrared ray. These are the way that we can visible. For example, ultraviolet light can be visible in the vacuum, and infrared light you can be visible in the like a remote or infrared. That's one simple example. So coming to the Einstein, so what he said, electromagnetic radiation falls on a metallic surface and it will pass through electromagnetic force. This is the basic concept of quantum computing. Though based on these, before that, everyone proving that energy having two ways. One is electromagnetic and radius. Next, the main concept called as dual split. What is this dual split? The brain of this dual split is Young. The scientist called Young identified the dual split where the light is incident on a surface. It is having two, it is moving in two directions. One is on photon, another is on electromagnetic wave. So when light is showing a particle nature, it is considered that light traveling in form of photon. When light is also showing the wave nature, it travels as an electromagnetic wave. That is the difference between the two waves it is passing. Okay, the area where the dark particles appear, it is in the terms of energy. Okay. So before the Planck's constant and postulates of Planck's constant, I want to explain what are the fundamental principles of quantum mechanism. Principles of space, time, a Galilean principle of relativity, Hamill's principle, Wave's principle, probability principle. These are all the principles of fundamental quantum mechanism. As I explained, light travel in a dual nature. One is shown in the photon, another is in the electromagnetic wave. Okay, this electromagnetic spectrum is the range of all type of electromagnetic radiation that energy travels and spread across out of the visible light. Okay, hope the concept is clear. For example, the visible light that comes from the lamp in a house, and the radio wave that comes from the radio station. These are the two types of electromagnetic radiation that we can notice. Okay, hope the concept is clear. Okay, so now I was explaining that the energy will traveling in a when light is traveling in the form of photon, and energy is traveling in the nature its form of electromagnetic spectrum. So what is a photon? What is a neutron? What is an electron? So these are the basic concept. It is in electromagnetic spectrum. So I want to understand what is a photon. Okay, let me explain what is photon. Photon is found in an atom. When there is a positive changes in a nuclear atom, we call it as photon. Similarly, neutron. As the name says neutron, there is no change. There is no change in found in any neutrons of an atom. We call it as a neutron. Similarly, what is an electron? If there is a negative changes and it is surrounded in a nucleus of an atom, is called as electron. So now I'm here to explain what is Planck's constant. See, the Planck's equation, E is equal to h and v. E is equal to hv. E is the energy, h is the radiation, and v is the quantum, and h is the constant. Here h is the Planck's constant. Here the word quantum energy of photon came into which is the constant, the Planck's constant. That the overall equation is called the quantum energy of photon. The frequency of radiation, and where E is equal to h into v. V is the quantum energy of the photon, where h is the Planck's constant. Okay, where E is the energy, h is the Planck's constant, and v is the frequency of the radiation, and c is the speed, and mu is the wavelength. Okay, lambda is the wavelength. So there are three postulates of Planck's quantum theory. So there are three postulates in the Planck's quantum theory. One is on energy is not continuously radiated or emitted. As I explained, energy is radiated, here ejected. No, energy is not always continuously radiated or emitted. That is the one principle or a postulate of Planck's constant. It releases a minute quantity of quantum or energy packets. That is the second rule. And each radiation particle is referred to as a photon when it forms a light. So these are the three postulates or a principle of quantum, Planck's constant. So now I'm here to explain. By this we have understand what is quantum mechanism, what is a classical quantum, what is a physical quantum. Okay. So now what is a quantum? A quantum is what is a quantum? Can anyone? It's a discrete quantity of energy. That's it. It is a discrete quantity of energy where the magnitude to the frequency of the radiation is present. It is a proportionality in magnitude and radiation. Okay, that is called quantum. So here, what is quantum computing? It is the area of computing. The quantum computing is the area of computing that level up the principle of quantum mechanism. The process of fundamentally different, varying compared to classical computing. This is completely different than classical computing. In quantum computing, we have superposition. As I said, superposition. That is one of the big advantage in quantum computing. One is superposition allow quantum bytes, or called as qubits, to exhibit superposition of both 0 and 1 continuously. That is called superposition. Okay. Hope the concept is clear. I'm just focusing on basics concept of quantum physics and classical physics, and now jump on to the quantum computing. Here is a beautiful example where quantum computing have a superposition in nature. It can behave, it will behave. See, here is a beautiful example. This is called quantum computing, where in the left hand side, it is moving on both state, 0 state or 1 state. We all know that computer having only 2 bytes, 0 and 1. In a state, for example, in a NAND gate or a NOT gate, either the output can be a 0 or a 1. But in quantum computing, we will have both 0 and 1 at the same time. That is called quantum computing. This the process, the computation is in parallel. That is the difference between the quantum computing and normal classical computing. Here, the concept is clear. Okay, let me explain. So as I explained, superposition. Superposition is derived from classical computing. For example, let me explain. In a classical computing, we have byte 0 and 1. As I explained, 0 and 1. But in quantum computing, this bytes or qubits, what we called as, that can be in both 0 and 1 at the same time. That is what it is showing. From here to here it is moving. No, it is having both 0 and 1 at the same time. That is the major component of quantum computing. Okay, because this makes the computation more faster in a parallel process. Okay, this is one of the key features of quantum computing. Next, another was entanglement. So as I said, entanglement. So when 2 or more particles or 2 or more objects are connected in such a way that if there is a change in one state, the whatever the changes that appears, it is also reflected in the another state. The same changes is happen. We can easily calculate it without knowing without computing the changes in the another state, because both are connected, both are entangently connected. This is how the pictorial representation of entanglement. As I said, 0 is a state, so it starts from 0, 0, 1, 0, 2, so 0, 2, like that. If the changes has happened in this is 1, this is in one state, this is in one object, and is in another object or in another state. If there is a changes in one object, one state, we will easily identify what is exactly changes in the other one without knowing the information of this state, because both are connected. No, that is the power of entanglement. Okay, so now quantum computing framework. What is the conventional computing? What is quantum computing in a universal game? What is quantum computing in quantum analysis? See, we have a language, machine code, and gate or processor, what you call, and transistors. So based on these 4 components, we're going to identify what is this conventional computing and quantum computing. So in machine language, we have the like bits, no, 0 and 1, and also the processor we can call as microchips or semiconductors, so transistors. So these are the components of the conventional computing. Coming to the quantum computing, we have a quantum gates, qubits. So qubits are circuit that we have two at the same time. Here it is a X gate and H gate is connected. So I'll in future slides I'm definitely explain what is these gates are and what is the processor that you're using. As I said, circuits or a gates that is using H gates, poly gate, Hamilton gate. So these are the gates that is differ from the conventional gate to the transistors or a processor what they used. Okay. So these are the qubits, and this is how the difference between the conventional computing and quantum computing. In future slides, you will definitely understand what exactly it is mean. What is the history of quantum computing? How this quantum computing? This is from the quantum physics, the theory or fundamentals. What I'm explaining here is from the basics physics. As I said, the brain or mastermind, a superman of this quantum computing is Planck's. In the year 19s, only the Planck's constant came into picture, that is called quantum hypothesis. In 1935, equilibrium harmonics came into picture. And 1964, Bell's inequality. And 1970, a birth of quantum information theory. 1988, first conference on physics and computing. 1981, Fleming's quantum computing proposed. Similarly, in 1982, Binord's quantum tuning machine. And 1984, quantum cryptography. 1985, Texan universal quantum computing. And 1994, Shares algorithm. Shares and Bowers is the main algorithm that we found in quantum computing. In future slides, I'll definitely explain what exactly this algorithm also is. And 1996, and the race goes on till 1994. We have a circuit, quantum modes, demos, and transformers, D waves. 2007. Different companies are bringing their own quantum computers or quantum computing. For example, here D-Ware, Digit, Microsoft, Google, IBM, Icon, now Honeywell. So these are the companies where the quantum computing is ongoing and the more advantage or ongoing advancement is happening till 2020, 2007, 2022. This is the roadmap or like history or a the background of the history of quantum computing from the year 90s. Okay. Here is a simple example of what is classical computing in a different state. As I said, quantum computing have, so in generally, we have two states, a 0 and 1 state, only two states, 0 and 1. In what is in classical physics have, I'll show you how the gates works. See, in classical physics, this is how, when the 0 it comes now, only 1 is respond and it stops. It has only one state, up and down. No. Similarly, what is happening in the quantum? So the wave nature of light, this quantum having the wave nature, no wave particle, that radiation, magnitude of the frequency of radiation proportional to the frequency is proportional to the magnitude of radiation. That is the core concept of quantum. That is how it is working. It is present in both 0 and 1 state. That is called superposition state. This is the best and good example of what is the difference between the classical and the quantum computing. Okay? Hope the concept is clear. Quantum state. So we have 0 and 1. Only by a computer can understand only two bytes. One is 0 state and 1 state. See, what if T0 and T0? These are the different gates that can support. Here I'm bringing one use case. For example, a single process execute. If a single processor execute multiple operation one by one. So it is like x0, 0. At x0, the point will be 0. At x1, 1, 0, 0, 1. And x2, 0, 1, 0. x3, 0, 1, 1. So similarly, there are 7 bytes because this is a 3-digit number in a binary state. So each is having one session, one by one. Okay, this is a single processor which is passing one by one. Similarly, we have a multiple processor which is execute multiple one processor within a one by one. For example, it is in a multiple, it is in a sequence. It is one by one. Here the use case for this is a single processor executing a multiple operation. Here it is a multiple processor execute multiple operations simultaneously. And third use cases I brought a single with a combination of both. A single processor execute multiple operation at a time. For example, f of 0, it will execute after only one processor is required. A single processor that will execute multiple operations. This is how the quantum states. how does it looks? So today's session, I'm also explaining on hardware of the quantum computing. How does it looks? This is how the quantum computers or quantums cubes or looks. It's a vacuum cube. So in cylinder A, this is an image of the cylinder, where in this cylinder where the quantum processors and cooling system is placed in the system A and D. These are the one physically we can see that. This is another example. So these are the cylinders, like it's a crystal state. It's a crystal state where the quantum processor and cooling system is placed, and we can see B and C. So this B and C is the system for which inside the cylinder there will be power supply, cooling gas, control box, processor. So these are the place. This is in the C and D, the gates and processor. These are the circuits. So this is how the quantum computer looks, the hardware. Okay. It's a vacuum. It's a cylinder in shape. And second is the circuits that will connect the power supply and cooling gas and control box. This is how the quantum computer looks. So what is inside that cylinder? We were so curious on A and B, C, D. So there are big container in this slide. No, very big containers. These are the cylinders. No? Moving back to see. So these are the big cylinders. So what is inside that cylinder? Want to understand what is inside that cylinder? So inside that cylinder is a lot of cable connected, a multiple layers separating from disc-like separation. So we can see one is another disc. What happened? Hello? Hello? Hello?
Now it's
Okay,
fine.
let me
Now
continue.
it's
Yeah,
fine.
sorry for the interruption. Let me continue. So how the cylinder looks like? There are multiple layers, like a lot of cable is connecting. No, from one layer to another way, it is bifurcated. This is how the inside the quantum cylinders looks like. So here exactly in this image, the more important part is missing is that the processor, that the quantum processor is missing. These are all the cables. These are the cylinder. Inside that cube cylinder, we have all wires is connected with the disc separated. No, with the disc separated. So more than the wire, the quantum processor are missing. So that I'll show you. This is how the IBM. This is one example of quantum chip. This is how the processor. This is integrated in the top. So this is how the quantum chips or quantums are integrated. So this is connected to the external cable. So these are the so this is also connected with the external cable, and these are the discs separated from one wire to another wire. And these single chips form one chips form a multiple ports chipset. This is RF port connected to the chipset. This is how the visualization of the quantum chip. Okay, this is how it is connected to the quantum chip physical behavior. Why it is segmented? In this example, I showed it is a cylinder, but there is no chip. Why it is segmented? Why it is one after the other? Because we have multiple layers, like layer 1, layer 2, layer 3, and it's separated. No, these are the wires and these are separated. No, that last item is called chips. That is called quantum chip. Okay. How it is connected to the external world? See, this is an example of this is the cable, and this is a cylinder in shape, cylinder cube. Inside that, this cable separated disc. No, this is how the wires are connected. See, this is in this example. A zooming of this image is this. So we can see in the all the wires, and these are the way it is integrated, means circuits. And last is the integrated chip called quantum chips. This is integrated. This is connected to the external. Okay, this is how it is connected to the world, external world. We can see how does it looks like in the end user, the end system. It looks like this IBM system. This is one of the processor with the quantum computer, quantum chips. This is how if I open this space now, if I open this, it will look like this. This is how it looks in the outside world, how it looks. So if I go deeper into inside this, we will see the wires and disk, and the top bottom is for a quantum chip. Hope the concept is clear. So as I said, there's a cooling machine, no? Inside that cooling machine, how cold should it be around the quantum chip? See, because quantum chips are maintained in a very freeze manner, very cold temperature. The most required cryogenic cooling to the milking range, very close to the absolute zero. It is very close to absolute zero. It is reference to absolute zero of minus 270 Celsius. Superconducting quantum computer, one that use superconducting circuits. So these are the way how the cooling factor will come into cool this entire cylinder with a quantum chip. Okay, and one is superconducting, one is a semiconductor. It's like a silicon chip, no, silicon based quantum computers, and another one is trapped ion quantum computers. These are the way that we can cool the quantum chips. Okay? Classical computing and quantum computing. So now, after understanding a quantum physics or a classical physics and how the hardware parts of the quantum is looks like, now we'll jump on to what exactly the classical computing. What is classical computing? How do you compute in the classical manner? We know that bytes 0 and 1. How do we compute? For example, a 3 bytes, a 3 digit of zeros, 0, 0, 0 indicates 0 state. A 1, 1, 1 indicates the value 14. Okay, sorry, 15, 15. In a 3 digit, we have 1, 1, 1. In the binary representation of that one is 15 in decimal. For example, 1 into 2 to the power of 0 plus 1 into 2 to the power of 1 plus 1 into 2 to the power of 2. The summing of all is called a 15. The decimal number, what in the front we see, in the front end we can see the decimal number that will be decoded in the binary digits is called 111. That is how the bits can be integrated. Next, I move to gates. How the gates? Logic gates, circuit gates, AND gate, OR gate, XOR gate, NAND gate. So these are we understand in the classical computing. No, we understand. We have learned how the circuit is integrated. Transistors, logic gates. Next, that transistor we will understand what is an algorithm. So basics fundamentals of any computation is called algorithm. Algorithm is a set of instruction that computer can perform based on the circuit design. Based on the circuit design, how the circuit behavior, the input from the any gate, logic gates, for example, 0, for example, in the AND gate, 0 and 0 gives output the 0, 1 and 1 gives output the 1. This is how the computation performs based on the gates. How this gate is derived from bits. See, it is a one process, the bits followed by gates, the gates followed by circuit, the circuit followed by algorithm. These algorithms are now into the application. So that is called the structure of a classical computing system. We are all studied how the classical computer works based on the bits followed by the gates. The input of the gates is the bytes. The input of the circuit is a list of the gates, and similarly, the input of algorithm is a list of circuits. A large and n number of thousand millions of circuits form an algorithm, and more gates form a circuit, and similarly, a 0 and bytes form a gate. This is how the flow of any classical computing system. Similarly, when you come for quantum computing, the same technology, the same method is applied for quantum computing. The quantum bytes, what's called QUBITS, a quantum gate, same. Similarly, like in classical computing, we have a gate, the quantum gate. Similarly, we have a circuit, the same algorithm we designed from the quantum circuit. That algorithm is performed. The same algorithm, like for example, algorithm, a basic algorithm is search, a linear search. A linear search, a binary search, okay, logic. These are simple algorithm. And similarly, that algorithm have the application form. That is the saying the classical computing is work like a quantum computing. The only one difference between these two is in bytes we have one state at a time, only one state at a time, either 0 or 1. There is only one state at a time, either 0 or 1. But coming to the quantum bytes or QUBITS, we have 0 and 1 at same time. 0 state and 1 state at the same time. That is the only difference between the quantum computing and classical computing. This makes the system so faster to computing, because if both the states 0 and 1 are the same, but no, this computation appears in parallel process rather than for series in the 0 and 1. That is the big difference between the classical computing and quantum computing. Hope the concept is clear. Let's move on. What is qubits? Qubits means bracket. We say the notation in the qubits is called as bracket. First is bra and second is gate. Bra means if I open, so the inner product of Q. See, before understanding this qubits or any quantum computing, we need to understand linear algebra. That is also a basic foundation for quantum computing. When you perform operations like vector representation or a scalar multiplication, addition, vector addition, scalar multiplication. These are the basic principle of linear algebra. I hope everybody has studied what is linear algebra, how the behavior of the vector representation in addition, subtraction, multiplication behaves, and similarly a scalar representation in addition, subtraction, multiplication behaves. That's a basic concept of any mathematics, any computing. For example, in computation, we will understand how the vector representation. With that knowledge and only I'm moving that, we all know that what is a vector. So the inner product and outer product, inner join, outer join. So similarly, write the inner product as bracket U vertical V. Instead of writing U or comma V, the quantum bytes are represented as bracket U. This is called 1 byte, and slash comma V bracket is called another byte. So we call this as slash vertical slash comma V as a kite. Means this is a kite, and U, sorry, bracket followed by U comma vertical is called as bra. This kite, which is an element of vector space of V, and similarly this bra is an element of dual space in V. This is an imaginary. Okay. Similarly, we have a bra and kite. The bra is from open. This is a greater than bracket U followed by vertical. It's called a bra. The indicator of this notation of this qubits is one is bra and second one is kite. So it's vertical followed by variable bracket. So this is called kite, bra and kite. These are the two notation in quantum qubits. So as I explained, bra and kite. The vertical it's great less than or over, and this is a one state followed by vertical line. This is another, for example, this is a 0 and this is 1. This is a mu and this is a xi. Mu and xi. So the bar is followed by bracket. So bracket followed by vertical is called a bra. Vertical followed by bracket means greater than mark is called as kite. These are the notation we call it as in qubits. Okay. So this is how the 8 digits. So it starts from 0, 1 to 1. Xi, as I said, 0 state. This is for 0 state. It open for 0 plus 1. If I add this point, this and this, it will give us 1. This is the first state, 0, 1 to 1. And this is 1 by root 2. 1 by root 2. Second state, 0, 1, 2, 3, 4, 5, 6, 7. If I see 0 and 1, similarly 0 and minus 1. This is both are 0 and 1. Here 1 and 0. Similarly 0 and minus 1. 0 and minus 1 and 0. These are opposite in direction. These are positive and negative. These are another state of positive and negative. How the opposite is 45 degree. At the 45 degree, I mean second state, 1 by square root, 1 by 2 square root, and 1 by 2 square root. 2 states. How do I represent in a qubits? Xi is 1 by square root of this 0 byte, and 1 by square root of this 1 bytes. Okay. This is for the 45 degree. Similarly, for the second state, 0 and 1, I have 1 at the 0 state and 0 at the 1 state. Okay. Similarly, the negative of this is 1 by square root and minus 1 by square root. Okay. Xi of 1 by square root of at 0, 1 minus 1 by square root of this. This is opposite of this. This is 1 by square root and this is 1 by minus 1 by square root. Similarly, we have opposite direction. These are the spin of this qubits. Bytes, how this byte is bifurcated. Okay. Similarly, we have a quantum bytes at 1 byte. As I said, 1 byte. See, this is a bracket. So this is a bra. This is a bra where 0 state have 1 and 0. This is a 1 transistor. We have a 1 byte. It's called 0, 1 and 0. Both at the same time. That is the function of the QUBITS. At 0, we have 1 and 0 both. This is how it indicates. 1 of 0 indicates 1. This is the 1. 1 no. At 0 state, it is 1. At 0 state, it is also 1. Okay. Both are present. That is called 0. In leftmost 1. Okay. And second state, it is 1. So 1, 0 and 1. It is 1 and 0 here. It is 0 and 1. This is a 1 byte example. This is a 1 byte example where xi is equal to 0 at the 0 state, 1 at the 1 state. Okay. Here 1 at the 0 state, 0 at the 1 state. Sum of these two. Sum of these two form an all 0 state plus beta of 1 state. This is called cuboid state. The square of these number indicates the probability of spin exhibit 0th state, and this probability of this spin exhibit at 0th state, 1 state. Here the alpha and beta are the complex number. Just imagine this is a complex number. The xi is a complex number where alpha at the 0 state and beta at the 1 state. Okay. This is how the 1 byte, 1 QUBITS, 1 quantum bytes. Similarly, for 2 quantum bytes, I have 2 bytes. 0 and 0 is a 2 bytes. Now 0 and 0. If I have 0 and 0 to 1 and 0, if I multiply with 1 and 1, because 0 indicates 1 and 0 in 1 byte. No. In 1 byte, 0 indicates 1 and 0. Similarly, if I go for 2 bytes, no? If I multiply these, 0 indicates 1, 0. It is in a vector representation. It is in a vector representation of the 0 byte is 1 and 0. If I multiply 0 and 0, 1 and 0, that gives a 1, 0, 0, 0. Okay, if I multiply this is a product of. Similarly, if I have the 2 bytes at 0 at first state and 1 at the second state, 1 and 0, I multiply with 0 and 1. 1 indicates the 0 indicates the 1 and 0, 1 and 0, and this 1 indicates the 0, 1, 1. If I multiply this 0, 1, 1, 0. This is the, how do it represent in a 2 bytes, 2 QUBITS. Okay. Similarly, I have 1 and 0. Similarly, 1, what is 1 represent? 0, 1. 1 represents 0 and 1, 0 and 1 vector. Multiply with the 0. 0 represent 1 and 0. If I multiply these two, this is the outcomes. 0 and 1, 0. Similarly, for 1 and 1, 0 and 1 for 1, 0 and 1 for 1. If I multiply these two, a vector multiplication of these two gives an output of 0, 0. Okay. Here we have a 4 outcomes from these 2 bits. 2 QUBITS, we have 4 outputs. Alpha, beta, gamma, delta. This is the probability where spin exit at 0, 0 state. Alpha is the probability. And similarly, beta at the 0 and 1. And gamma at the 1 and 0. And delta at the state 1, 1, 1. So we are seeing no spin cycle. This is how the spin cycle. When we have a 2 bytes, 2 QUBITS, alpha, beta, gamma, delta. These are the probabilities that the spin exhibits. Similarly, the vector representation of this probability function is xi is equal to alpha at 0, 0, alpha at 0, 0. If I multiply these with the alpha at 0, 0, beta at 0, 1, gamma at 1, 0, and delta at 1, 1. Alpha at 0, 0 plus beta at 0, 1, gamma at 1, 0, delta at 1, 1. These forms called as probability function at QUBITS byte is equal to 1, 2 bytes, 2 QUBITS. Okay. Hope the concept is clear. When I coefficient all this probability specific bytes combination gives us alpha square plus beta square, gamma square plus delta square. Sum of this is always is equal to 1. Hope the concept is clear for 2 bytes. Similarly, let me explain for 3 bytes, 3 QUBITS. I have 3 bytes, 0, 0, 0. 0, a vector representation is 1, 0. A vector representation of 0 is 1 and 0. If I multiply this with the 1 and 0, 1 and 0, this indicates 0, 0, 0. If I multiply these, the outcome is 1, 2, 3, 4, 5, 6, 7, 8 digits. Because it is 2 to the power of 3, na? 2 to the power of 3. Bytes still 0 and 1, 2 bytes. 3 bytes, 2 to the power of 3 is 8 digits. Of the concept is clear. Similarly, if I have 3 bytes, 0, 0, 0 and 0, 0, 1 gives out outcome of this. And 0, 1, 0, this is the digit 2 represents. So 1, 0, 0, 1, 1, 0, digit 2. Then similarly 3, 4, 6 and 7. As I said, 1, 1, 1 indicates 7. So this is the 0, 1, 0, 1, 0, 1. If I multiply this with the 3 digits of in binary, the outcome, this is the QUBITS. So this is the this is a kite. This is a kite of 110. This is a kite under 111, 3 digits, 111. So the outcome is 0001. This is how the 3 bytes representation in quantum, that is called 3 qubits. Hope the concept is clear. Okay. So this is just a yes.
Hello, ma'am, can you explain that multiplication? Yeah, how we are getting this that output?
In a vector representation, if I multiply 1 with the 0 and 1, 1 into 1 gives us 1, 1 into 0, 1 into 0 gives us 0.
Okay.
Okay. Similarly, if I multiply 1 with this outcome is multiplied again with this. So what is the outcome of this? 0, 1 and 0. If I multiply 1 with the 1, this is the output. And if I multiply with the 0, 1, this is the outcome. So if I multiply with the 1 into this and this is the outcome. If I multiply with all this is the outcome. Okay.
Okay.
This is a visual representation, pictorial representation of bytes in 1. If qubits is equal to 0, if the qubit is equal to 1, and if the qubit is equal to 2, what is the qubit is equal to 0? 3. This is a representation by what 0 and 1 bytes. Okay. Till now I explain. No? That will be summarized in one slide in the video. Okay. Hope the concept is clear. So as I said, qubits having some properties. Let me compare this qubits with the classical computation. For example, in classical computation, here I'm taking a Euclidean space, like a 2D Cartesian space. So in a Cartesian space, if I describe the classical space with, if I compare with the quantum space, I can have a 3-dimension in any classical computation space or in a quantum like a Euclidean space or a Cartesian space. I have only 3 dimensions. When I compare the quantum or a helmet or a state space, there is infinite dimensions. It is an infinite dimension, and this Euclidean or what Cartesian or classical computing works on a real number, but it works for quantum work for complex number. Both have the inner product. So similarly, I'm explaining vector addition. So just now, madam asked now how do the multiplication or a product of these 0 and 1. No? This is the property. When I add R1 plus R2, that gives the R3 in a real number. So if I multiply with the xi1 with the bracket plus xi2 with the inner bracket with xi, no, not xi. It's a no, it's not a bracket. It's a xi. Xi means first vertical followed by bracket is a xi. Sorry, K, not Z, K. Xi1 at K state, Xi1 at the K state plus Xi2 at the K state gives the Xi3 at the K state, which is a complex number, which is not a real number. In vector algorithm, we have a real number. In quantum, we have a complex number. This is one example. Both behave the same, but it is work for real number. It is work for complex number. This is how the vector addition or vector scalar multiplication works. The same nature behaves in the quantum world as well. Okay. A of xi3, it belongs to complex number. Okay. For example, A of R is a property of real number. No, A into B into BR of is a B into AR of R. So this property is also true. For example, A into B into C is equal to A into B into C. If I one in bracket, first 2 bracket and second 2 brackets. No, that is also same, like A into B into Xi means it's a kit. A into B into kit. Same. This behaves that this says that the property or a nature of quantum qubits is same like a Cartesian or a classical computing. The only slight difference is natural classical computing work for a real number, where quantum work for complex number. Okay. Now quickly jump on to gates. So these are the gates available, or these are the gates worked on quantum computing. One is polygate at X, polygate at Y, polygate at 0, X, Y, Z gates, and Hadamard gate. Hadamard gate is one of the well-known gates in quantum gates. and control gate is or a X NOT gate. So these are the gates. For example, this pulley X gate works like a NOT gate. This is one input and this is an X gate. This is a NOT. Okay, similarly Y gate, and in future slides I'll definitely understand what is exactly pulley gate and pulley gate at X, pulley gate Y, and Hamilton Hadamard gate. Okay? These are the basics gates in the quantum gates. So for example, pulley gates. Pulley gate is a quantum gate at X. Pulley gate X is 0, 1 and 1, 0. This gives an output at the 1 at 0 state, 0.1 at the 0 state, and this Xi 0 at the 0 state and 1. Some of these two gives us the output of this. This is the gate. If I go with the 0 and 1 and 1 and 0, 0 and 1, 1 and 0, if I multiply with this Xi at this state, this is a function of pulley gate. So this is the outcome. So if I multiply this, 0 and 1 comes. So this is the output from the pulley gate. Similarly for Xi, 0 and 1. This is for 1 and 0, and this is for 0 and 1. This is a pulley gate X. Similarly, pulley gate Y, as I said, pulley gate Y is an imaginary number or a complex number, not imaginary. It's a complex number. I is a complex number where -1, -1. So sorry, it's not a real number. It is an example of imaginary number. I is always indicated with the imaginary number minus I plus I at state 1, 0, 0 at 1. So this is how this Y multiply this gate Y multiply with the Xi. This if I multiply with Xi, this is the outcome 0 and 0 and I, 0 and I. 0 indicates this is multiplied with 0 and 1 indicates if I multiply with 1. Okay. Similarly, this is at second state 0 at 0, 1 at 1. This is an example of Y gate followed by different state Xi at 1 and 0, Xi at 0 and 1. Okay, this is for the gate Z. So here it is a negative value 1, 0, 0, 1 is a Xi gate. If I multiply this Xi gate with the 1 at 0, 0 at 1, this is the outcome you can get. Okay, 1 and 0, 0 1. So this is the Z gate. If I multiply this 1 and 0, the outcome will be the 1 and 0, the same one. So if I multiply with 0 at 0, 1 at 0, 1. So if I multiply this, I encounter with the 0 and 1. This is the gate. This is a function of gates at poly Z. This is another gate called Hadamard gate in a quantum gates. And Hadamard gate where we have 1 divided by square root of 2, 1 divided by square root of 2, 1 divided by square root of 2, minus 1 divided by square root of. This is the basic gate for the Hadamard gate. If I multiply this Hadamard gate with the 1 at 0 state, 0 at 1 state, this is the input 1 and 0. The outcome we can predict. This is multiplied with 0 and this is multiplied at 1. If I do the computation, this is the 1 by square root and 1 by square root. If I multiply this with this is the outcome. Okay. Hope the concept is clear. This is another gate called Hadamard gate at H. This is an Hadamard gate. This is at the point 0 at 1, 1 at 0. If I multiply these two with the 0 and 1, at the Hadamard gate, the input is 1 by square root, 1 by square root, 1 by square root. Minus 1 by square root gives us the 0 and 1. So this gives the 1 by square root and minus 1 by square root. Okay. Hope the concept is clear. Similarly, for 0 at 1, 1 at 0. Let's move on to quantum circuits. So this is the basics. We have Hadamard gate here, no? Hadamard gate Q1 at state Q1. This is the bytes Q1, Q2 and Q3 gates bytes. I have an Hadamard gate. An Hadamard gate, if I do the computation of Hadamard gate, this is a signals indicator. This circuit gives us the value. Hello?
Okay.
Hello?
சரி நூலகன்னா என்னது?
Now I'm explaining the circuit. As I explained, bytes followed by gates, gates followed by circuit. This circuit is a combination of both the bytes, This is the input of bytes and the gates. That this forms a circuit. The matrix of this H gate, no, as I said, this is the H gate at 0 and 1. If I multiply 0, 1 and 0 at 0 and 1 state at the H gate, Hadamard gate having 1 by square root and minus 1 by square root. This is the matrix of, this is a vector representation of Hadamard gate. If I multiplied 1, 0 at 0th state, 1 and 0. Similarly, if I combine 2 bytes, no, 0 and 1, it is at 0 and 1, and this is outcome from 1 at 0, and this is an outcome from 0 and 1. Okay. And similarly, if I go for the NOT gate, for time being, this is a NOT gate. This is a NOT gate. So I didn't explain NOT gate. So just understand how the combination of the circuit is designed using one H gate, means Hadamard gate. The function of Hadamard gate is 1 by square root and 1 by square root and minus 1 by square root. If I multiply this is the outcome. Okay. Similarly, if I combine the another gate at 0 state, at 1 state, no, it is at 1 state, 0 and 1 is the value. If I multiply 0 and 1 by 1 by square root and 1 by square root, this is the outcome. Okay. Cross product. Okay. This is how the X gate at the beginning of Q1, for initializing the Q1 as one cat 1. This is a cat 1. So if this is the original circuit, this is a transmitted circuit. At 0, 0 H means Hadamard gate. At 1, 0, this is the X gate, means poly X gate. And 0, this is the outcome. This is then integrated with the 0. This is the outcome, and this is an outcome for the 0, 0. Okay. Similarly, the same will be transmitted. Okay. This is how the formula alpha square plus beta square gamma square delta square is equal to 1 when bytes is equal to 2 bytes. As I explained earlier, this is how the state. So in the histogram, we can see what is the percentage of 0 and 1 and 1 and 0, means 1 0 here and 0 1 1, 48% and 50% in the histogram representation. Similarly, this is another circuit called HC0 circuit with K1 and K1. So 1 and 1. For example, if H is hammered gate 1 and 0, things it's the same. It behaves the same. Okay, 1 and 0 gives us 1 and 0. But when I matrix for the H0 gate, 1 by square root of 1, 2 gate bytes 0 and 0, and minus of 1 by 2 to 1 and 1. So this is the histogram representation. This is another circuit gate for H0 with 1 and 0. This is for HC0 with 0 and 1. This is all the mathematical operations behind. If I add H and H, means Hamilton 2 times, no, 2 times of these gates H and H. If I have one Hamilton at 1 and 0 state, at 1 and 1 state, so actually this is an H Hamilton at 1 and 1 state, not 0. This is a mistake. It's 1 and 1 state. If I have a 1 and 1 state, no, by 1 and 1 state at the Hamilton, this is the outcome. This is the outcome I can draw. Similarly, 1 and 1, sorry, this is the mistaken. So this is for 1 and 0. This is for 1 and 0, not 1 1 1. And that is for 1 and 1. This is for 1 and 1. This is another circuit for Hamilton C0 gate. Okay. This is another example of Hamilton, two circuits, H and H circuit at 0 and 0 state. Okay, at 0 and 0 state, Hamilton H and Hamilton H. If I apply this product, I can draw this Hamilton having 1 by square root of positive and negative. So means 0 I, 0 minus I, no, that is a combination. So 1 by square root and 1 by square root, 1 by square root minus 1 by square root. This is a matrix representation of Hamilton. So if I multiply with 0 and 0, if I 0 input and 0 input for the Hamilton, this is the product I can draw. When I compute, when I integrate or I combine with the two gates, this is the outcome. Okay. If I multiply these two, row operation into column operation, row wise and column wise. Row wise means 1 by square root into 1 by square root multiplied by 1 into 1 by square root. The sum of these two plus sum of these two. That is the formula that we have did. That is the vector multiplication that we got. 1 by square root whole square. This into this is square. This into this is square. Plus this into this into this is square, and this into this is square. already the one person has me, the earlier one, she asked me that how do the matrix multiplication occur? This is a one best example. I multiplied 1 divided by square root with 1 divided by square root. This forms a 1 by divided whole square. Similarly, I multiplied 1 by square root with the denominator with the 1 by. It's a row versus column operation. 1 by square root into 1 by this gives the 1 by square root whole square. Similarly, if I multiply with the second element in a row like 1 by square root multiply with the column like 1 by square root multiplied with 1 by 1 square, this is the outcome 1 by square root whole square. Similarly, if I multiply 1 by square root, if multiply with this 1 by whole square. So this is how the matrix operations, the multiplication operation of a matrix performs. So if I combine two at Halmerd gate at the state 0 and 0, this forms one circuit. This is another circuit. Okay, this is a simple example how two states of two Hamilton behaves. This is an Hamilton gate of 1 and 1, state 1 and 1. This is when I have two circuits, two Hamilton circuit at the state 0 and 1. For any circuit drawn, the input is a byte, another one is a circuit, another is a gate. One is a Hamilton gate. Here, for example, I use Hamilton circuit 1 and 1, state 1 and 1. So if I multiply with the Hamilton gate at one state means 0 and 1, one state means 0 and 1. This both are same. If I multiply and add these and this, the same exactly the square. Because here it is a negative and here is a negative. That's why if I multiply these and this gives a positive. If I multiply these and this gives a negative. Okay, got it? Similarly, we have in quantum computing, we have quantum bytes called as QUBITS. I explained QUBITS 0 and 1, bra and gate. If I open bracket followed by vertical line called a bra, vertical line followed by a bracket is called a gate. So two state, 0 and 1 state. So the logic of quantum computing is the both 0 and appears at the same time, bra and gate. That is why this 1 and 1 appears at the same time. Similarly, after bytes, we have a gates. So gate is a input for the gate is the bytes 0 and 1. So similarly, if you have 0 state and 1 state, how this gates are being performed. Similarly, the input for next is followed by circuit. After gates, next is circuit. This circuit input for the circuit is the bytes and gates. So this is how this circuit is formed. This is how the hierarchical structure like bytes, gates, circuit. Similarly, this is another example for a circuit, Hamilton gate at 0, 0, 1. This is a 3-byte example. When we have a 3 bytes, 1, 1, 1 and 1, 1, 1. Okay, the fourth step of this, any computation, a classical computation or a quantum computation, we have algorithm. First step is bytes, second step is gates, and third step is circuit, and fourth step is algorithm. We have an algorithm. So quantum, there are many algorithms for searching and binary classification, binary bifurcation, linear search and exhaustive search. These are the different searching techniques. So in quantum algorithm, we have initial stage in the year 1985. This is how the history of this quantum algorithm came. After this, bytes, gates, and circuit is formed. One is at the initial stage. The problem of quantum appears in the year 1985. See, dept and Simmons, these, and along with the Zohar and Shor, these are the algorithm. It's a famous algorithm for searching and sorting techniques applied using quantum algorithm. So Zohar and Shor are the two major algorithms bring in the quantum computation to solve the problem, complex problem like searching and sorting, a binary classification. So these are the problem. These are the way the quantum computing came into the picture. So it is increase the performance because it moves in a parallel state, both 0 and 1 at the same time. That is how the Zohar and Shor algorithm came into. I didn't explain how this algorithm works. It is not in the scope of this session. That is why I specified on bytes, circuits, and gate only. this is a just example of how the algorithm, because one and followed by others are integrated of each other to make any applications. So this is one example of how the algorithm for quantum computing perform over the year. Okay. The first is initial state, and second is a quantitative chain state, and third is a quantum algorithm for big data environment. And in 2014, the quantum algorithm for NISQ era and hybrid quantum or classical algorithm based on a variation in quantum circuits. This is how the era of different algorithm comes. Majorly, quantum still now the major algorithm for the quantum algorithms are Zohar and Shor. These are the two algorithms which solves the linear search and binary search and sorting, linear sorting and binary sorting. Okay. This is another example of era of here is an example exactly. So here are different algorithm. So here I'm just not giving them more detail of what exactly the algorithm. Just one in the year 1985, Dutch's algorithm, Dutch's Zohar's algorithm, Shor algorithm, Siemens algorithm, Grove algorithm, Grover's algorithm, quantum Fourier transformation, quantum phase estimation. These are the different algorithms, and what is the description of each algorithm. For example, let's consider this 1994 Shor algorithm. It's a famous algorithm that is majorly work for factorization of a large number. Exponentially, it is faster than classical computing. Okay, and similarly, Gore algorithm, it is quadratically more speed. But Shor algorithm gives an exponentially faster. Similarly, a Gore algorithm gives a quadratically faster than classical computing. This is how the different algorithms work for quantum. From 1985, before I born, 1985, the era of my parents, that from there to till 2014, the different variant of a quantum algorithm was formed based on that problem has been solved, based on the different problem. Once this algorithm formed, what is the application? What is application? What is an application? So here, this is an application. See, industries having multiple problems. So these are the where quantum computing marked up. For example, a user's level and application level or software or operation level or CPUs or QPUs levels and final level. Is this? Okay. So the different markets or different industries looking for quantum based on the material science or like a category for supercomputing or a cryptographical levels. These are the companies where the quantum computing are now enrolled across the globe. Okay. This is how the industry looks for quantum computing. Similarly, what is the hardware and what is the power required for quantum computing? So what is the hardware required? There are several approaches to build a quantum computers. One is the hardware that is required for supercomputing qubits, trapped icon, topological qubits. What is superconducting qubits? It is used like IBM, Google, and other, which that depending more on superconducting circuit to create a qubits. And trapped icon, these icons are trapped in electromagnetic field and manipulated using the lasers to create a qubit. This is called trapped. So these are related to how this quantum computer are built in computers. Okay? And third is topological. We all study what is topological. It's a more theoretical approach to creating qubits that is less prone to the error. So that is called topological. So these are the way the hardware has been derived. Similarly, what is the computation power that is required for any quantum computing? It's a single byte. For a single byte in a superposition can represent an exponentially larger number of states than a single byte. So what is exactly the power supply that is required? The system for n qubit can represent 2n into 2 to the power of n possible states. Okay, simultaneously. This leads to a quantum speed up for a specific type of problem. See, we have a because this quantum working in a parallel, it is more exponentially faster than classical computer, more quadratically faster than for classical computer. We saw more algorithm like Zohar and Shor. Based on this, these are the power supply and hardware requirement. quantum computing. So this I already explained. That's it for today's session. I'm open to answer. Initially, I told you to. These are the introduction. These are the links that I can share you to reach me. I mean, there's a scholar. This is scholar and LinkedIn, GitHub, and ResearchGate. That's a scholar gate. So, thank you all for the session. And now the session is open for discussion. Initially, I told you to it should be interactive, where I explained one matrix, that is the operation of it's a multiplication operation of two vectors, how it represents. Yeah, now the session is open for discussion. If you want anything, or can close it. So the concept is clear. This is a very solid concept. It starts from the quantum physics or a classical physics, and how this hardware looks, and how this computation like a classical computing perform, and similarly how this quantum computing perform in the notation of bytes, gates, and circuit, and how this forms an algorithm, and what is application. I forgot to tell what is an application of this quantum gates, this quantum computing. We have multiple applications. For example, let me recall. For example, in the cyber crime, this quantum computing can help in the cyber crime, like cyber threat identify based on the AI or machine learning base. And also, for example, drug development, this quantum computing that will accelerate an exact of drug discovery. In the finance modeling also, this quantum computing which will that use the model of financial marketing. And in the cryptography also, this quantum cryptography, these are the different applications. For example, cyber security, drug development, or quantum cryptography. These are the way the applications looking forward based on the algorithm of quantums. For example, in the cryptography, quantum computing can be used as a mechanism of secure and transfer the data in a way that unhacking way. That is called cryptography. In also weather forecasting, like quantum enhancement technique that improves the predicting weather, the weather forecasting that will improve the predicting weather by providing more accuracy results. So, for example, even in the application like a traffic optimization. This quantum computing can monitor traffic in real time. So that is one example. It is very robust, very effectively. These are the way the applications of quantum computer can apply. We can look forward in future also. It's ongoing invention in multiple organizations like IBM, majorly on IBM, more focusing on quantum. So they released more quantum computers, and also Google, Microsoft, Amazon. So these are the companies, they are bringing more computing power, work on computation, more on quantums. By this, hope the concept is at least somehow it is understand from the scratch of physics till the application level. Think.
Good evening, ma'am.
Huh.
Ma'am, it's audible?
Yes, Miss Ma'am.
Good evening, ma'am. Thank you so much for your wonderful session, ma'am. Really, it's super, ma'am. So we get some knowledge about, before that, we don't know about that quantum computing. So after this session, we get some knowledge about quantum computing. Thank you so much, ma'am. Ma'am, I have some doubts about that. So that is
to be frank, this is the area which is very new for me too. Even I googled it and researched
really
it.
super,
Bring
ma'am. It's
for you.
eye-opening.
Yeah,
Really super. It's an eye-opening session for us, ma'am. It's creating interest to learn more about this topic.
Yeah.
Thank you so much. So my doubt is how quantum computing is differ from parallel computing. This is one question. So another one is you shown that a lot of algorithm that is machine learning, the quantum machine learning algorithm you shown in that algorithms you shown in that tabular column, no? So you specifically shown that quantum machine learning algorithm. So how it is differ from ordinary machine learning algorithm? I have two questions, ma'am. Hello.
Yes, ma'am. I'm just sharing my screen. See, first I need to answer first question. One is how it is differ from parallel computing. As I said, let me share my screen. This is what, okay? First, I need to answer your first question, how it is differ from parallel computing. Parallel computing, we have superposition. That nature we call as superposition, like that computation goes parallelly, not like a conventional sequentially. The same is in quantum computing, but the one major change in the quantum computing is entanglement. If there is any change in one state where both states are interconnected, that same changes is appear in the another state. So that is a major advantage of supercomputing, not just only the superposition. Superposition is if it's a parallel processing where both 0 and 1 is computing, performing, both 0 and 1 computing should happen at parallel processing. Along with the other features of quantum computing is one is entanglement. If there is a change in one state, if both states are interconnected, that same appears in another state. That is the one beauty of quantum computing. And second question I want to answer this quantum machine learning. So we all in the era of artificial intelligence. So what is a machine learning? First of all, any model that can train in the machine that will work independently without any human interruption based on some training data and followed by test the model. So this is how the machine learning performs. As I never dig out or never understand how this quantum machine learning algorithm, based on my understanding of this, I can understand this quantum mechanism, as I said, just superposition and entanglement and inference. This concept, if applied in the machine learning, what is the machine learning core mathematics? It is a linear algebra, and where equation of a line y is equal to mx plus c. That is one simple computation that we perform using machine learning model. It's like a linear regression or a logistic regression function. If I use this quantum computation technique in the machine learning, that will definitely speed up, or it will potentially speed up our any problem like as explained here, classification or clustering or feature selection technique. That quantum is just used for the computation purpose, not for a class machine learning only. If I club these quantum with a machine learning, that will definitely speed up this computation task. That is the only algorithm we are here. So other than that, if something I missed and something I made a wrong information, I'll definitely do rework and definitely come back to you. This is what my level of understanding. So that's why I explained. If I made any mistake, please do apologize to me. I'll definitely go to the literature and come back, because this is not my area of expertise. Anyway, I am here to explain the basic principles of quantum. Hope the concept is clear.
Yes, ma'am. Thank you so much for your valuable information. Ma'am, can you give me your contact mail ID?
Sure, madam. Sure, madam. The coordinator will definitely share. We will definitely. You can reach me at any time. We are here to share our knowledge and learn new things from you and others. So we are here to learn new things only, no? But definitely, I always like to learn the things from anyone. Open for it. Keeping up upgrading my skills.
Thank you.
Anything from anyone? Hope the concept is clear.
Kirtana, ma'am. Kirtana, ma'am. Thank you, ma'am. Thank you so much for your session, ma'am.
Thank you, sir.
It was a wonderful session.
Thank you so much, sir.
I think Sarah's joined. Manjaya Sarah's joined. Sir, good evening, sir. Manjaya, sir.
Good evening, Professor.
Yes, sir. Good evening, sir. Good evening, sir. Ma'am, Sumitra, ma'am, you can find up, ma'am. No issues. You can stay online, ma'am. No issues.
Thank you, sir. Thank you so much for your for the opportunity.
Okay,
Thanks,
thank you.
everyone.
Okay, ma'am.
Dropping from the call.
Yes, ma'am. Thank you, ma'am. Thank you so much. Uma, ma'am.
Okay, sir.
Sarah's joined. You can continue.
Okay, sir. Okay, sir. Thank you for your wonderful session, ma'am. Thank you. Now we are having the second session. The topic is quantum ubiquity, harness quantum computing for a seamless digital future. Here we are having the resource person, Dr. Manjaya DH. He is presently working as a senior professor and chairman in the Department of PG Studies in Research and Computer Science, presently acting as a Dean of Science and Technology, Mangalore University, Mangalore. Previously, he worked as a director of BMEB and Rusha coordinator. He has done his PhD in the area of advanced network computing paradigm with quality of services and performance analysis. He completed his MTech from National Institute of Technology, Karnataka, Surathkal. His individual involved in teaching and research more than 30 years. He has produced very valuable 22 PhD scholars who are all currently working in reputed organizations and educational institutions in India and overseas. Presently, 8 plus 2 overseas scholars are responsibility research under his supervision. He has technologically progressive the original knowledge of routing algorithm for mobile ad hoc networks, vertical handoff mechanism for 4G networks, and augmentation of digital forensic laboratory in India. He also has vast familiarity of handling large-scale research projects sponsored by various funding agencies like UGC, DST-SERV, and DST-VGST. He is highly held responsible and principal investigator and director for recently received rupees 20 crore project from the BMUSHA, Ministry of Education, Government of India, for the further amplification and development of both research and academic activities in Mangalore University. He has delivered more than 235 invited and keynote talks in several international conferences, symposiums, workshops, and training sessions in India and abroad. He has authored and published around 167 in reputed international national journals and conferences on various topics in mobile ad hoc networks, IP version 4 and IP version 4 mobility, machine learning and deep learning, virtualization using cloud computing, cybersecurity, and digital forensics. Presently, he has above 1,077 citations and 17 H index and 27 I-10 index. We are having such an eminent person for this session. Now I hand over the session to Dr. Manjaya. Sir?
Oh, okay. First of all, very good evening to all respected professors, faculties, and the research scholars. I think my voice is audible, Professor?
Yes, sir. Audible, sir.
Yeah, fine, fantastic. I hope shortly, because evening sessions are moreover correct now. Somehow computer is going to take a break and ours is going to be think some sort of the zeros and ones. Probably, hopefully you can understand. And my sharing PPT is already I sent. You are going for that one, or shall I share the PPT directly?
So you can share your PPT, sir.
Okay, fine, fantastic. Just 1 minute. You got it? You are
No,
viewing?
sir.
Huh?
No, sir. It is. Yeah. Yes.
Now you are viewing?
Yeah. Your screen is shared.
Clickable, no? No problem. Shall I proceed? Professor?
Yes, sir.
Okay, fine, which are going to be. Okay, fine. You're okay, all of you? Comfortable?
Yes, sir.
Okay, fantastic.
Thank you, sir.
I'm so happy to see around 100 and more than 140 participants. Probably my slides also very going to be somewhat dreaming. I can learn many things from you people also. See, way back 5-6 decades back, man-made machine, directing a machine, and finally you are seeing a digital paradigm. What not which are going to be happen. A computer basically what you call a commonly usable machine. It's an optimal one, it's a materialistic one, it's a highly powerful one, it's a better performance one, universal one, and probably uniqueness one. And ideas behind is like a taskable one and efficient one, highly resourceful one. But we are moved towards the technology aspects because computer never understand any languages, computer never understand any sort of what we are sending through our ideas and the innovative, but which are going to be converted in the form of zeros and ones only. Best. But what that's a meaning of digital. What is digital? Say data, exchange flow, idea which are come from the our sensible organs. And finally, we are moved to the different type of a man-made machine, this is data. A intense competition, a globalization, a God internet era, technology, automation, and least cost and high productivity. What we are seeing today, but still further enhancement, which are going to be take place, nanotechnology and various type of a technology, but the machine may further a computing power, which are nothing but a compute, correct? Now, what are all the changes? We'll go one by one, what the changes, and basically I'll give a very brief introductory and finally move towards the standard level of the algorithm, where which are going to be applicable, adaptable, then we'll go one by one, state of the information. And if you have any inquiry, please kindly raise your hand, raise your voice at any moment. And meanwhile, better, we appreciate the end of the session is always better because we are through more than 1,000, nearly very close to 600, 700 kilometers virtually connecting, and we are finding a lot of other catastrophic events also present since 3 days due to the effective unsurprised cyclone. But anyway, no problem. We used to manage because of the computing of the quantum. Ladies and gentlemen, exactly what you come, because we know very well various type of a computer, but what is meant by quantum computer? The mechanism, what is a phenomena, correctly, you have to understand the operations. We have seen various, suppose you take a simple configuration of a computer and 3 important components are behind it. One is a speed that automatically say what the speed. My speed is very high, the computing speed is very low. Correct? Today you are seeing we are seeing the level of Intel chip, AMD processor, and Motorola chip, Ericsson chip, whatever it means. Correct? Our cellular partner also providing various type of computing techniques to perform the various operations, especially you see that one operations involving not only the simple operation like arithmetic operation performing in the level of applications data through device such as superposition, what Madam earlier speaker told and given yesterday also, entanglement, basically providing such a way that understanding the level of MIPS, millions instruction per second, and megaflops, we can say million floating point operation per second. Above that one, you can say, is it possible to go through that one? There's a concept behind it, quantum computing. And especially if you see the generic idea, a basic binary computer, correct? No, we have seen that one because they made up of a certain a transistor type of a, correct? No, components, basic electronic components, what we come up like a gates, which are going to be understand and take the values of not more than plus or minus 5 volts, correct? No, in order to glow state of the 0 and 1, what do you mean type? You can understand the traditional computer, the binary state, calculating entirely classical mechanism which are behind it. But still further, if you move towards what we can understand, and especially the speed applicable, correct? No, today the paradigm of the processing, progressing is entirely different, correct? No, the Moore's laws, we keep correct now, keep on changing the doubly, the exponential level of the progress, exponential level of the increasing paradigm, which are ultimately provide some sort of a thinking capability, and we can make sure, correct? Now today I'll give an example, simple example. Even though in a home, in a village, in an urban area, not only users are going to be get connectivity, and where you are moving and walk to, similarly through vehicles, and not only that one, in our home also pet also want to see the world like God internet, but we are finding a deficiency of the address, not now, because not only you have to be think about our country 140 crore very close to the population, but in addition to the living organisms, correct, no, who are maybe available, want to see that one, you can say the atoms, molecules, ions, whatever it may be, want to get through that one computation power, then that is going to be providing excellent level of programming, and as well as a paradigm is basically called the quantum computing. And serial processing operation at correct now, because everything going based on the serial sequential manner, but you can another end you can see the parallel processing mechanism, 64-bit classical computer operation speed. We are not in a position to understand like a 2 power of 3 8 also, and 2 power of 4 16 also. If that is the case, how it's going to be 2 power of 6 level of the representation at a time within a short span of a time, and within a short span of a nanosecond or a picosecond, 10 power of minus 9, 10 power of minus 2, point followed by 9 zeros or point followed by 8 zeros classification which related, but how which are going to be powerful. See, especially to harness the power of atoms, correct, molecule for memory and process. Today you can see in any application, you take a medical application, and similarly, correct, transcription especially, how the operation which are going to be performed, correct, no, doctor is not a god, but anyway, the powerful computational and powerful level of how the complexity, especially the complexity like a time complexity, space complexity, whatever it may be, we are studied thoroughly in a computer science and generalized, but how best way which are going to be make use for the application oriented. The parallel processing like a millions of operations at a time in the sense per second you can take per unit of representation. But with respect to the quad, we can say the quantum computing is a bit of operations which are going to be perform the power function like a exponential function in teraflop, 10 power of 12 above that one, trillion of floating point operation. I mentioned very clearly earlier also, the configuration machine basically consists of like one is a speed, another one is a RAM, third one is basically holding the capacity, disk storage of that one. If you make that one, you can classify the computer like a mainframe, mini computer, supercomputer, and simple computer, whatnot, but which are just for our understanding. But application oriented, like a one is called a RISC-based machine, another one is a CISC-based machine. What is RISC? Reduce instructions set per computing paradigm. Another one is a complex set for computing paradigm. See that one, the basic state of an information in a quantum bits, classical as well as observing very clearly two states of an information, correct? No? You observe whatever the value representation like a 0, 2 power of 0, and similarly 2 power of 1, correct? No? The value of the representation, what we understand thoroughly, the state of an information of a classical bit. But which are going to be represented in the quantum bits called a qubit representation, superposition of both states, correct? Now combined together, we can get the value of the representation highly and get through that one, like combination of 0, 0, 0, 1. If you go with like a 3 bits level of the representation, 3 zeros, and finally 1, 1, correct? Now the value of the representation. The basic fundamentals which are managed such a way that built-in predicates on the system itself only. The one of the important things, significant feature of why you, correct? No, always worrying about the computing power and the quantum computing power, especially the factorization mechanism, correct? No, today you are going like a power of like a 1, 2, 4, 8, 16, correct? No, 32. Then you can go with like up to 2048. The combination of that one is 2 power of 12. How the representation? But is it possible to make a representation with a simple calculator, simple laptop, or a simple desktop? But the built-in predicates of the device with itself only perform the level of number of bits, correct? The n number of bits of the representation is basically providing integer factorization. Quantum database research, probably we have come across like today, you can see the applications of that one, Google search, Amazon, Alta Vista, Hotbot, whatever it may be, search engines, applications which are available. Because what is basic motherboard required for providing an extensive knowledge of which are going to be processing and which are going to be displaying and easily observe on that one state of an information with various other activities, correct? Is it possible? And not only today, this one, classical computers built in, which were long back story like a century, and quantum computer in half a second, correct? How the performing the searching option which are going to be, we observe that one time complexity is very, very much more understandable and highly reliable. And usually some of the important applications we can think about, like practical applications which are going to be provided not only in a computer science, all 360-degree angle, you look at like a business, commerce, whatnot, which are correct now, physics, chemistry, material sciences, components which are basically how we can set up how the smart, correct now, city, some sort of a project which are MEMS, which are like micro electromaterials related stuff, so whatnot, correct now, where exactly can find the better soft core, hard core, which related stuff, so with the help of a standard level of a paradigm using a practical application of quantum computing. Like a computer can compute millions of variables at once, correct? All limited today by a slow speed quantum mechanism simulation. But one of the application which related is interdisciplinary, you can say otherwise a multidisciplinary. We can make use for any sort of an application combined together in addition to the applications as well as various basic science also, and applicable with respect to the standard problem we can easily solve with the help of quantum computer. And another important feature today, we are finding like a lot of various problem, attacks, fraudness, defaming, and generally, correct now, and various plagiarisms related, not only plagiarism, you can think about like cryptocurrency related aspects, how the standard like a blockchain, these are all one of the standard. Basically what will happen, you are not in a position to find a person who is going to be make a fraud within a location local, but how you can find a person who is making more than 1,000, 100, 2,000, 10,000 kilometers of the distance. And these are all basically providing an extensive knowledge. That's a crypto analysis capable of cracking extremely complicated codes. Basically what we learn like RSA algorithm, DS algorithm, message digest algorithm, but still further we can go with standard level of how the key management, correct, primary key setup with the standard 200, more than that one, 200 digits of the representation of that one coding theory concept we can make use with the help of quantum computer applications. And basically you have to see the history, because the mystery what we are observing today with an application, not only from today, and basically from 1973, 1976, these are various, how the changes which are went on, and finally you are flooring and understanding the level of NMR computing paradigm, IBM standards today available, still further enhancement of that. When I don't want to take the history, because way back, in which way a simple computer with a different type of a revolution, different type of a generation, like that way, the basic idea behind it, like since 1973, and later some of these various proposals and how the various type of approaches which are went on, finally, like working of 7-qubit of the NMR computer, and later also you can find out various other. In the supercomputer also, Param Padma, Cray 992, and VAX 8810. These are the various standard supercomputers available. Suppose anybody would like to visit the IASC campus, like a supercomputer lab, there you can see how the level of the approach today. Unsurprisingly, we are getting like various catastrophic events which are happening, because how is it possible to save this data and predict such a way that something is going to be in future days after correct now sometime, and where this data is going to, because of this quantum computing ultimately providing a better solutions. And what are the candidates for quantum correct now today? I told very clearly, superconductor based quantum computers and squid level based quantum computers, ion trap based quantum computers which are available, and nuclear magnet, various type of base, because the application which related how we can make use for the different type of discipline level and factorization level and the application level, there you can make use and understand the concept. And some of the important problems today, what we are observing, like a current technology, like a 40 qubits of operating machine needed to be current classical equivalent, correct? Now you can find out, especially various type of erroneous factor used to be find out. And is it possible to find the solution for finding the error detection and the error correction with the help of quantum computing problem? Just I'm giving some of the applications, correct? Not able to redo properly with respect to the various type of the application. Is it possible? Of course, you can take a standard level of the machine, which is holding the level of quantum computing paradigm. There you can make use and realize, correct? Now, some of the research I don't want to go, because some of the standard research references which are there, especially what we observed so far, computing paradigm, like you take a simple laptop or a desktop or a palm top, whatever you go to, base level of like a decimal and the binary, and the operation which are going to be take place within a short span of a time, but we don't have a control at all. But to see the operations, what we observe, basically, I don't want to go all this thing, but in order to understand the operation which are going to be performed easily, correctly in the form of like various, but get into the level of what the standard level of the size capable to handle the power function which are related, correct? Now you can say that was shown as Intel processor today, like i3 is there, i5 is there, latest generation super speed of the different type of quad core is there, dual core is there, correct? Now the performance of that operations per second. So imagine like 1 into 10 power of 9 of this. That means to say, in terms of giga level of the operation which are going to be performed in second. And more than that, correct? Now you have like Intel also 3, very close to 3 into 10 power of 9 operations which are going to be. But these are the composing with none other than the electronic component transistors only. A typical size of a transistor, what we have said, a picture like not more than 0.04 millimeter, correct? Now the representation. But how this one is going to be propagate, simulate with respect to quantum computing, you can see that how far you can this one, correct? Now I mentioned very clearly the scale of the transistor rapidly growing, correct? Now you see that one, how the changes in a, correct? Now how representation in the form of exponential, very close to probably, hopefully, like synopsis standard level of the application which are available, and you see the various approaches, the changes which are going very close to the y-axis also, plus and minus and whatever it may be, more or less. When the integrated level of a superior, correct, microprocessor circuit was first made in tech, correct? Today, what we are observing, our cellular phone also, like various type of Texas Instruments, and then later, which are keep on multiple that one in terms of twice, two times of that one. Then what it shows very clear, blue line shows the prediction of that one operation in the form of how we can, in which way the year of the an x-axis, and similarly how the transistor which are going on the other end on y-axis. And this size is keep on increasing, embrace, correct? Now you can observe it's a better way of qualitative analysis and increasing of computational power. So some of the standard principles which are behind it, because any sort of a system which are going to be handled depending on the ethics and the myths of that one. But you look at like they have their own standard principle. No, you take a simple a quantum uncertainty, which are going to be the velocity, correct? Now, how the our movement. Observe such a way that which are going to be looked at and where my chances of to take an opportunity, correct? No, but that is an uncertainty option. You have a look how it's going to be, find out its state of an information. Similarly, the probability that something is going to be off state or something going to be on state, you can say according to our understanding, like 1 or 0, 0 or 1, sometime until which are going to be observable or non-locality of the entanglement, because some of the standard principle approaches which are behind it in order to design a quantum computing paradigm. These are the standard level of principle which are basically. If you make a comparison with what the existing classical computer as quantum physics which related, correct? No, outcome of that one, correct? No, generally predicted outcomes and which are going to be provided a different classical laws scale values which are there. And if you see the discrete and the variable state of an information, in order to understand the concept of application oriented, take on finite known values, because which are going in the form of infinity, not the infinity in between the value of representation, but superimposition, which are going to be provided representing all states of an information, which are going to be thoroughly understand the concept in between off state and on state, and intermediately which are going to be measured. If you see that one, how the level of representation throughout and which is going to be within the level of correct now available space itself only, you can find out the flow of an information understanding thoroughly. And the binary system, especially what we can understand like a qubit, especially the quantum computing, the base model is a qubit, represent the binary system in quantum rather than classical state, carried as an atoms, ions, photons or electrons, which going to be represent the respective control devices that are working together as a computer memory and a processor. See what we say that one, like internal memory, external memory, extendable memory, what primary, whatever it may be, correct? No, in order to go for understanding entanglement and allows multiple numbers to be represented simultaneously with the help of qubit only, because qubit is a base model which are going to be understand for how we can basically providing a quantum computing approaches. Sorry. And generalize. You take a classical bit, one is a 0, another one. If you go for the 3-bit representation, you see that now the space of an information which are available beginning from 2 power of 3 representation values. Correct. Now we can do that one. One is on state and generalized. But how the computing paradigm which are going to be work, what we are using for the today's computer, correct? Now we have to be very clear and always remember Turing machine mechanism, correct? Now finite automata, definite, correct? Now deterministic finite automata approaches, which are thoroughly providing how the manipulation of state of an information finally you can easily carried out. But in case of quantum computer, you can see that one limited of 2 states, and we can observe various other level of the information which are in the form of a qubits and which can impose superposition and provide a level of the correct now between same type of an information, and which are going to be provide a million computation within a short span of a time. If you take like a supercomputer, whatever it may be available, we can through correct now you can easily measure, but the superposition of the level and value of the processing with the help of superposition, which are going to be a million computational or operation which are going to be performed within a short time period, and we can prove that. A simple like how we can return the concept or the convention which are going to be focused, like superposition number can be written as like value ups and down, correct? No? On state and the arm state, and the expanded further, we can see that one how the value which are going to be take place. Just a look, correct? Now we have representation where 0, 1, 2, 3 simultaneously represent, used by comparison to classical computer. What used to be observed, like the level of the value, like only two states of an information, we can find out two different. And still further, a quantum data representation with respect to design of that one, correct? Now is a set single electronic transistor, a 0 or a spin up or a spin 0, correct? Now spin down value of the representation, not today, which were observed long back from the Harvard University, followed by like how the transistor which are going to be taken to each other perform the operation. And quantum dot now and later, correct? Easy to make and operate because you can come across easily, understand thoroughly how the operation which are going to be performed, and which are very, very tiny inside, because small inside, dealing with because of what we can not able to see, that when ions, so atoms, so electrons and photons, and which can pass apparent rapidly, and also which are going to be perform phenomenon decoherence, and which are going to be happen within a microsecond, 10 power of minus 6 value of the representation. And still further, you can go with a comparison with the transistor can retain the state. How many of the years been already. And the, some of the standard level of experimental basis, how the computation which are going to be performed, like a binary is the lowest level and ground state. You see that these are all the state of an information, physical realization of trapped ions, how which are going to be performed as per the standard of NIST, correct? National Institute of Standard Technology, trapped to the storage group, and currently which holds a record of 7 qubits. So these are the operations which are going to be performed 408 nanometer in the figure above what it shows. I don't want to be explain those things. Trapped ions now and later, difficult to make a operate and use in scale because enough enhanced level of the scale of representation, a laboratory to make more than 7 systems stable, and which these are the state of an information which are available, and size and speed also very, very unimaginable. Today, quantum computers have the state of an information enhanced like a 16 qubit computing paradigm, like what we have like the various state of an information, and basically future aspects of the quantum computer which are going to be performed like a factorization, and we can make use for the large database fractions which are going to be enhanced, and also application could be enhanced further in terms of mechanics, say the atom, molecule, ions, whatnot. You can just see a waveform of the generation, you can easily observe there you can. And interesting, some of the correct, no, all we come across very clearly how the prime numbers which are going to be factorized, correct, no, basic idea behind it like cryptography, because how we can make use the crypto analysis, and similarly digital forensics mechanism, and some of the standard current quantum time to factors and the classical time to factor, the value of the order of the value representation, and a great personality like a Peter Sharp, correct, no, how a polynomial versus exponential time calculate, and similarly speed of which are going to be in case of quantum computer more methodological and more precise and more concise and better accuracy. And check out once again, which are like a trillion years factors, 5,000 digit number, a quantum could finish within 2 minutes of the operation. Imagine quantum computation is more powerful than any sort of a classical computation, even including like a supercomputer, because more can be computed within a less time. That is the time complexity for doing more operation. Just I'll go with like a some of the history which relate to perform like a laws, what are the mechanism which are behind it, like a behavior of practice, especially the atoms, ions, photons, all particle, which are levels of that one. Basically 1982, two, the proposed idea behind a creativity, innovative mechanism based on the laws of quantum mechanics, physics, laws which deals with study. And later, in 1985, David developed a quantum figuring equation, because in which way the growth which are behind, and you have to way back understand the concept of that one, the changes which went on, like 1994, great Peter Shor came up with a quantum algorithm, very large number of polynomials. You can take like how the exponential function which are going with a variable, how the value of the representation, how we can easily find the rank root of the corresponding polynomial equation, which are easily through 1997, like once again, Grover developed a quantum search algorithm with an order of square root of order complexity, time complexity. And similarly, data representation, we specify very clearly state of an information like a qubit, a single bit to form known as a qubit. And physical application could use two energy levels, perform the operation state of an information representing and ground state representing 0, and another one state is representing 1. Exciting state of an information, like how the flow, which are going to be understandable, basic idea behind it. Once again, the superposition in both state of an information simultaneously at the same time, which are going to be perform the operation, and that is super representing of data superposition. Once again, if you take an example like here, in which way the 3-bit of qubit to the register, which are going to be performed, like how the standard level 2 power of 3 once again is going to be 8, and how the performations of processing and the computational power of that one is going to be take place, and how the data retrieval, especially n number of qubit register can represent a number through correct now 2 power of n minus 1, and still further the randomly which are going to be find out the erroneous factor and the coherence of the value with randomly collapsing. Is it possible to understand the concept of some of the standard relationship among data entanglement, like ability of a quantum system to exhibit correlations between states within a superposition. Suppose you have a state of a 0 and 1, state of a 0, 0, 1, and similarly how which are going to be superimposed and perform the function relation, we can call it as entanglement. Entangle the two qubits such to be measured. One qubit is always correlated measure the value, the mapping of the function we can prove. Some of the operations we can easily understand, like a reversible logic which are behind it. Just you see, we have like a truth table, correct now, in which way the various truth table representation, but basically how the value of the representation which are going to be understanding, you must use like, if you go with like a representation of the gate, they must be reversible, correct? So understanding quantum gate similar to the classic gate, but do not have a degenerate output. See what will happen, which are going to be feedback original state of an information and find out the state of a unique level of data composition. And finally, what it means to say is a deterministic computation, computation which are going to be performed with a quantum computer, and luckily we can find out the value of the deterministic state of an information. And as per the reference of like a great Charles Bennett, 1973, this is a paper how we can prove that one. The simplest gate involves one qubit called a, see, you can observe very clearly how the changes which are going to be successfully carried out the operation. If you perform like a NOT gate with a square root, how the operations which are similarly control NOT, what we say like a tilde NOT, and that is going to be like what is operations are going to be performed with the target of that one. See, these are all the operation multiplication by 2, because 2 power of the functional value, how the simple operation, just how the operation which are going to be handled with the help of a control and control NOT CCN gate to perform the functionalities. Similarly, universal gate operations also, and some of the standard algorithm with the help of all the things. You can say a principle behind it, finding the capable of factorization. Suppose you take in terms of not going to be countable, understandable, a large number of representation of polynomial, how some of the standard algorithm depend on modular arithmetic, quantum parallelism, and quantum Fourier transformation. There you can use a standard level of the Shor's algorithm with the help of the quantum computer mechanism. Actually, if you take an example, important result of number theory, what we observe like a standard modulo value of the function, we can easily understand design aspects of that one. If it's more than that one, how n number of value of the representation which are going to choose an integer such a way that let's pick 256 value of the representation, how it's going to be. A depth analysis in order to understand, and there you can make use this Shor algorithm. And preparing of a data still further. If you take a total state of the system information using quantum mechanism, like a 2 power of 8 representation, 2 power of 8 representation, 256, the value is going to be in input register, the output register, how the which are going to be entanglement and perform the functionalities. Simple example like how the value of the representation of that one, which goes to be 7 modulus, correct? No, the power of the function with a modulo of the 15 value which keep on increasing. If you go with like a further enhancement, how the modular algorithm or the Shor's algorithm, you can make use in order to superposition, and finally you can get to the value of representation entanglement also. Because once the state of information, superposition and entanglement, various operations you can easily perform through this one. Some important Fourier transformation, correct? No, Fourier it might become across what purpose, filtering mechanism, you can make use Fourier transformation, and there you can easily use this type of algorithm, standard level of the algorithm. I don't want to explain because these are all the idea behind this Shor algorithm problem. In order to understand the qualitative of the Fourier transformation and the quantitative of the Fourier transformation, especially the application orientation in case of like a non-distributed distribution mechanism, there you can make it. And some of the important aspects which relates like a quantum computing, especially in the security implication. See, today we can observe like a Van Neumann architecture of the digital computer, correct? No, the level of quantization which are going to be observed through the quantum computer, the state of an information like a qubit, how the operation which are going to be built in predicate. See, you see the analog computer, I see the level, correct? No, parallel distributed processing neural network or the brain which are going to be formed. If see the classical computer, a digital computer, analog computer, but how the quantum computer enhance the level of the neuron level of the thinking capability, those are the changes. That is a figure what it says. What quantum computer can do, like a factor primes. Encryption algorithm, already we specify like RSA, DS algorithm, secure socket layer approaches to message digestive. These are all correct. No, what we observe, we are not in a correct. No, if you say 2048, the corresponding level of 2 power of 12 representation, how it is going to be performed, correct? No, 2 power of 12 of the 2048 value of the bits representation in order to understand the factorization. Similarly, quantum computer could do this minutes, correct? No, within a short span of time, less than 60 seconds. And secure communication, especially what we observe like a perfectly understandable, and today what we are observing, the eavesdropping and malware, correct? No, various other type of facing fraudness, similarly finding attacks. These are there we can easily make use the concept of quantum computing and find the problem corresponding solutions. Solve a variety of problems that are hard for a digital computer. Need not worry, because in order to manage such a way that harness of various type of problems which are available, unable to solve with the help of a classical computer, a digital computer, or existing computer, we can make use such a way that, because what we are finding a better performance accuracy, a supercomputer, whatever it may be, in order to manage and a prediction, we can say, and we can make use a standard level, solve quantum mechanical material, especially what we come across like a physics, chemistry, material science, biology, and business, wherever it may be, correct? Now, in a thin para mechanism, you can say microelectronic materials, whatever MEMS or SMEV, MEMS, whatever it may be, there you can make use a standard level of problem solving with the help of quantum computing. And how the working status, already I told you, the simple mechanism and how the observation of that one generally. And if you come to the standard level of applications, changes of the information because which are available to us, and enormous quantum power of the representation, enormous power, quantum of representation, because we come across very clearly in terms of giga, in terms of tera, in terms of qubit representation. There you can make use of power erroneously and find out the bit operation. Just you see, have a look how the quantum standard level of computing which are going to be performed with the help of a gate, simple gate. Suppose you're planning to go for a simple half order circuit, correct? No, we need like AND gate and similarly OR gate mechanism. How they perform? Binary values are represented by electronic signal, correct? No, you can make sure such a way that A value 0 and B value 0, similarly 0, 1, whatever it may be, operation which are going to be performed. And the representation we observe very clearly, and how the operation which are XOR operation which are going to be performed, the level of AND operation, correct? Now we have studied thoroughly, but this is going to be built-in predicate in case of understandable mechanism in order to set up like a full order or shift register or what we observe like a decoder, encoder, various, correct? Now operations perform, but within a short span of a time, how the operation which are going to be quantum circuit example. If you look at like a standard level of full order, which are going to be set up within a level of a simple and easy way to understand how the operation which are going to be perform the full order circuit operations. And you can say that for combo level of the model approaches which are available in case of quantum circuit example, how the operation which are going to be performed and find out delay. And so what we can understand, the concept is very simple. Computers can, we mentioned very clearly, in order to go for understanding the factorization and in order to go for help of searching and the unstructured database with the help of a Grover's algorithm. These are the base model of the quantum computer. And similarly, unbackable communication paradigm. Searching, then hacking, and similarly factorization. In addition to that one, various normalization process also can make use of that one. Quantum communication standard, correct? No, bipolar level of the digital representation, how these are how the operation which are going to be performed, correct? Now we can come across easily. I can take the state of an information, how which are going to be find out, like in case of eavesdropper, because the attacker, or similarly fraudness which are going to become in case of a communication system, how we can prove that one, we can find out. And fiction which related to be today more than a decade old, not today. Several companies today you can observe like a Geneva is there, and similarly Magic Technologies are there, some Seeker Net, what overall available, a private organization, commercialization, how they can scope for finding out the various applications of and make use some sort of a productivity and understand. Similarly, companies like today, Toshiba is there, Hewlett Packard, IBM, similarly some of the NTT, various standard research problems where they actively make use the applications of quantum computer. Dewey already like a quantum annealing computers, 2000 of a qubit operations which are going to be performed. IBM, Google, Microsoft, Intel level of the operations which are through, and we can find out like a race. Today, the operation basically like Ericsson, Motorola, overall not correct, no? In order to perform the operations more flexible and more predominant and contribution in terms of how the reducing and better accuracy, there they can make use of it. Intel announced 49 qubit chip of January 2018, and still further like what we say that one quad core, dual core level of the services which are true, and Google 72 qubit of the quantum computer in March 20. Still lot of development. These were the latest information what I got to you. And even China also satellite-based quantum key distribution demonstrated, like for especially for this one is for the military purpose. How they can make use for the especially for the confidential flow of the information there, like a 1,000 kilometer of the operation which are going to. And some of the deep standard level of quantum computers we can observe like a, because what we are seeing like a level of multiple number of processing capability, multiple number of memory related and whatnot with the chamber. It look like a D-wave structure of the computing paradigm. Whole system consists of the bus structure of that one and waveform of that one. How we can find out. In the IBM Atlas quantum computer have their own structure oriented, like in which we can find out for the application we can make use in terms of mechanics, physics and chemistry, biology application, and the weather forecasting applications in order to handle various. And IBM free quantum computer in the cloud today, what we observe like a arena of the emerging area like a cloud computing, and the IBM has seen have their own structure oriented the free quantum computer. The name of the standard, like they have their own landmark of IBM, and you see that one. These are all whatever the various, they have their own productivity, but we can classify three types. One is a quantum annealing computer, analog quantum computer, and universal quantum computer. How which are going to be performed? Basically, the application. If you look at like a least powerful, most restrictive form of quantum computer, which are going to be easy way of building, and similarly how which are going to perform a specific application functionalities. Advantages in the form of very conventional approaches and which are going to be understandable for a specific applications. If you see that the optimization problems, especially restricted, universal, and partial level of experimental observation, and computational power like similar to traditional computer in order to lower it, but difficulty level which are going to be easiest to build. Not so easy because annealer, especially we have to be specify what purpose application which are going to be. And bottom line is very clearly shows how what is the level of the solved problem. Client particular problem which are going to be conventional computer, and demonstration. Just I have taken this power of function, how which are going to be gathered within a short span of a time. And come to the analog level, simulate complex quantum interaction into various levels, which are going to be compared with the conventional computer, and conjectured that analog quantum computer will contain between 50 to 100 qubits level representation. The generality of the application, generally we can make it for chemistry, materials, and we have a Scopus level focusing more on MEMS, more on smart materials. So more on probably we have come across like how the operation which are going to be microbatch, a standard level of application. There we can easily make use. These are the, and some of the smart materials, their application which are going to be computations power billions of times faster than what we are using a conventional computer, and specifically for special problems. At difficulty level, moderately hard to build because you have expensive and you have to understand thoroughly what sort of application. And the most likely form quantum computer that will first to quantum speed up, and conventionally very high computing power. Apple the next future days also probably. And the third one is a universal paradigm, which is basically provide most powerful, most generalized, most integrated, very hardest building predicates of the tremendous number of challenges which are there in order to understand various applications. 8,000 is estimated, and today, correct? No, we have mentioned very clearly 2 power of 12, 2048 value of the representation. How we can crack, correct? No, 2048 value of the representation. Is it possible? There you can make the generality of the application like secure computing, and what we have come up with like crypto analysis, blockchain management too. And we can say that one generally like a Bitcoin application also we can make use one of the other. And computational 1 power many trillions of times faster than conventional. That means to say a generalized approaches, a time complexity is very easy to manage for the specific applications. And still further, like difficulty level extremely hard to build. Of course, in all cases, in all 3 different category or a classification of a quantum computer, always, and you have to take a challenge and go further enhancement of that exponentially faster than what we are using for the conventional traditional computer for number of various specific important problems. And still we are observing, like, of course this graph is a older one, like innovation trigger and peak of how the expectation of the value, and we see observation of the emerging technology hype of that one, in which the transistor, correct, not today VLSI very large scale, how the operation which are going to be that scale automatically scaling in computing, which rise in powers of like a 4-9 different angular representation, hopefully like qubits in computer nodes over past 5 years. There are no changes which are going to be take place, probably challenging which are there in front of us. We take like a first law, one of the important, instead of Moore's law, how the changes which are going to be take place in terms of application usage and in terms of how the predominant application management and how the qubit operation which are going to be performed for the challenging problems. This solid line shows very clearly where the gap is in between to understand the concept of value of representation, like a 4-9 value of the representation. Danger zone like bit encryption can be cracked. That means to say 2 power of 12 level of the representation which are going to be cracked with the help of, is very, very difficult to manage in case of a conventional computer or a small computer or a supercomputer, which are going to be possible in case of quantum computing. Post quantum world today, correct now? There is a very, very challenges which are in between us, a universal computer which are going to be managed. Most encryption used today is not safe in quantum world, but anyway, you have to be enhanced such a way that how the decryption level, correct now, which are going to be move further. There are encryption algorithms that are safe and how we can manage easily with the help of some standard structure oriented, harness oriented, digital infrastructure, and QUBITS computing, correct, various other approaches which come. Post quantum algorithm assessment. You see, observe, suppose various standard algorithm on the left side and the functionality, how we can make use, correct, no, with the MAC operation, hash function operation, signature, digital signature, key exchange flow, all the things. And is it possible how a pre-quantum security level which are going to be and post-quantum security level, the observation which are simple data, a gross algorithm, and which are going to be within a short span of a time. Similarly, Charles algorithm will pass this approach, various. Some of the thinking post-quantum now, like 5-10 years of the replacing, correct now? Today, like a set of instruction packages which are available, how we can find out hardness of that one, and is it possible to secure for the flow of an exchange throughout the world, correct now? These are some of the important, like just history further. We can just go through like a problem which are related in assignment, what I have given, taken state of an information. Further, helpful, like how the operation which are going to be multiple computations simultaneously, computing power is exponential index value representation. If you make a comparison with a digital computer and quantum computer, you can find out like a serial level or a synchronous level of the data, and even with the threads and the quantum is truly parallel level of computing, and which are going to be larger the problem, correct? Now, if you take into consideration some specific application, how you are going to be find the solution for that one, there you can make use of qubit. Power of algorithms, standard like a factorization, multiplication algorithm, in order to go for large computation, and quantum algorithm speed up the process, where you can make use all the level. Algorithms are very status of that one, like a sure and the other standard algorithm. Still further, like today we can see some of the standard machines which are available, understand, and quantum computing still further, like Theoretized and Richard and Peter Shaw and Tom Bell. These are, and some of the timeline factors which are behind, like expecting many within a short span of a time, how we can find out like featured imminent days, like years, faster than anticipated progress which are going to be, and just generalize like quantum computing in the cloud. If you take into consider like infrastructure as a service, platform as a service, and similarly, what we can see that one software as a service. And is it possible to make use like a arena of quantum computing in the cloud paradigm? Of course, you can through that one how the platform available in cloud, IBM Quantum Experience, which are going to be execute a standard level of an algorithm for various correct no virtualization, no load balancing, some of the standard algorithm correct no problem we have come across very clearly in cloud arena with the help of like some standard algorithms also and simulator also with the help of still further. If you take into consider like IBM Quantum, Q is called a quantum, is the new line of quantum computer which make you like a 50 qubits of the operation and perform the computation and the calculation power within a very precise manner in a cloudy arena. Similarly, first commercial quantum computers initiated from like IBM, say they are testing very standard level of 17 qubits commercial quantum computing, and later discovered how to the architecture which are keep on changing because the device once again the upgraded one like in form of 750 qubits. 3 years later planned to be reached. Then how the operation which are going to be architecturized later stage. Basic concept which are just I told very clearly. Features of quantum computer works with a quantum parallelism, entanglement, keeps in the coherence and the quantum bits of the representation which are going to be for various. The architecture is a superior one because in which way it goes in to understand the level of superconductivity and various bus structure in order to manage like how the signal, how the processing mechanism and supply whatnot which are going the interfacing mechanism all the like with a very standard types of computer processor we can say superconducting circuit to spin qubits to ion traps. These are various type of the quantum processor inbuilt how which are going to be very micro electro materials which are going to be perform the functions. And further circuit qubit and similarly superconductivity qubits which are their coherence time in superconductivity qubits managing, and IBM especially superconductivity qubit architecture which they like understanding concept like a 4-bit 4-bus level structure and now the 8 qubits and the 2 qubits level of the structure which are going to be the voluminous level of if you see in the structure of that one like a 3 isometric level of the projection of that quantum volume which shows very clearly understanding the performance of the computation in order to be visualized. Dilution refrigerator, correct? No? Generally, some of the applications which are working temperature like 15 kilo dilution represented, there also you can make use the application and the processor architecture which are available to us. We can just go through some of the layered architecture, logical. You see, once we can, in order to understand the processing mechanism, you can say that one how the physical and similarly input and output processing of the architecture and finally how the logical layer perform. You can say that one layer approach model understanding. Some of the algorithm I just specified very clearly, star algorithm, Grover algorithm, which are better we can make use for the standard level of an application and where you can easily carry some of these. And I don't want to just repeat once again. Quantum computing impact on application and industry. Correct? Now today what you are seeing, like we specify like a multidisciplinary and interdisciplinary type of approaches where you can make use all sort of and standard level of an application. And still further, you can see that one atomic quantum clock, a quantum sensor, intercity quantum link and simulator and various other. Correct? Now, hopefully, like 2035, and even though initiated like a standard emerging area like a 2015 and later, around 20 years, some changes which are going to be challenging operations and challenging performance and the application which are gathered and providing. And technology is very versatile, like you say, what we specialize like a sensor, quantum link, simulator, safe communication, provide a better free way of the flexibility of the freedom and universal quantum computer These are various type of a technological aspect which are behind it, and some of the experience which very clearly like composer and simulator, quantum processor, and community which are in which the predicates available to manage a standard level of operations, and especially the quantum operations which are through like one to another, like green blocks, blue blocks, orange blocks, blocks which are basically provide a structure-oriented level of data information with the help of qubits which are going to be provided operations. A composer, like working with the composer, you see that IBM quantum computing paradigm, the operation which are going to become, this is just a simulator, how which are going to be through that one. Similar quantum experience, how it works through various run simulative, correct now, you can find out like how the operation, finally for fabrication of that one, you can see that one, how the operation, and a structure oriented level of blocks which are through to understand and build a quantum community for users to be thoroughly, and these are the finally I can say that one classical computer reaching quantum scale need alternative to transistor technology. That means to say, even though we are coming from the vacuum tube, we are coming from the correct now very large scale integrated circuit, but mechanism, the problems, application which are available, and all problems very interesting, but how precisely, accurately, and providing a better type of a computational power, enriching, and is it possible to look at like a better than a classical computer, better than a supercomputer, then none other than computer, we can say quantum computer, which clearly, methodologically, and a standard problem invoking and focusing more on atoms, more on ions, more on electrons, more on photons. That's why quantum computer we have our own specific challenging problem around the globe. We can show that one. Finally, 7-qubit machine, we built a program, run successfully factorization of 15, and what algorithm will be discovered next? Probably NP might become across like what we studied, like the analysis of algorithm, a complete problem, a polynomial, then how the complexity we can understand easily through that one. Ladies and gentlemen, this might be which related to harness of computing and quantum computing, how we can thoroughly, if you have any sort of queries in order to understand, I can just able to answer, or else I can get back to you how we can get through the answer. Thank you very much for your an excellent opportunity, because within a short span of a time, you can't just get through that one. But anyway, I have given a glimpse of what is a computer, what is a quantum computer, what is a classical computer, and how the variations and the differences which are one to another. Thank you, one another. Thank you. Thank you, madam. Please kindly, if any of the queries, let me know. I can able to answer for them. Hello.
Hello, sir.
Please kindly let me know, Dr. Nirmala madam.
Yes, sir. Yes, sir.
Any
Sir,
sort of problems, any sort of questions, let me know.
Yes,
We can
sir.
able to answer, but still you don't have a problem at all. 8:30, still I can able to answer. If anybody want to do a quantum computing, correct now, problems are there research related, because even though we are always thinking about like a machine learning, deep learning, big data analytics, correct now, still further in order to understand the basic gates, is it possible to get the problems which related industry applications also, business application also, commerce application also, physics application, whatnot application which are available, we can do that. Please kindly make a note and let me know any sort of queries, madam. Thank you so much. It's my, because most of them are think about correct no kitchen side. Please kindly no, don't worry. But our correct no mental is also very important. How we can understand, because we are coming from the computing professional, but at least little bit knowledge is very, very essential. A basic USB level of the port connectivity. Tell me. Make sure. Ultimately.
Hello. Hello, sir.
Professor, tell me Kirtana ji. My voice is audible, no? Hello? My voice is audible?
Yes, sir.
Please kindly let me know. Request for the audience to open your mouth. Please let me know any sort of queries which related to just basic glimpse of the quantum computing paradigm. Please. Professor Ramarji, Ramar sir is available online. Professor?
No, sir. Sir is not available, sir.
Please tell me, Professor, any queries or else we'll see that one. Because I'm coming, still I'm in department only. I have to go to my home.
Yes, sir.
Please let me know. I have to travel nearly 25 kilometers from my university because I'm saying due to the problem of the unreliability, just I'm saying in department. Please kindly let me know. Please make sure good luck, all the best. And if any still further, I have my address is I think I have given. You can communicate me at any time. Will be available for your service.
Thank you, sir. Thank you so much, sir.
It's my pleasure, Professor. It's my pleasure. Always welcome to you.
Sir.
Tell me, Professor.
No, sir. If there is no queries, we can wind up, sir.
Oh, thank you so much. It's my pleasure. Always welcome to you. Please, I'll be available to you tomorrow up to Friday, Saturday. We have this one, the sessions.
Yes, sir.
Okay,
Yes, sir.
Fine, Professor. Please, kindly. I'm very thankful for your all sort of an arrangement. And once again, it's my pleasure to physically will meet virtually always. Correct? No, you have observed in which way the online things are going to be. But anyway, offline is always more reliable, more understandable, and somewhat thinking capabilities. Always best wishes to each and every one of you, and let me know. And once again, I'm very thankful to you for all sort of an arrangement you made, and still further best wishes for your continuation. ATAL FDP.
Yes, sir. Thank you.
Thank you
so
very
sir.
much, Professor.
Thank you, sir.
Thank you.
Sir, shall we close the session?
Yes, I'll be available because myself, if anybody is still online, I'll always be happy to answer, and probably we'll see that one.
Yes.
Please kindly send all the final, whatever the talk related records to me later stage, Professor, please.
Sure, sir. Sure, sir.
Okay, final of this, I think probable. Anything is kindly keep on touch with me because
okay, sir.
Through email and through WhatsApp, I will be available to you, please. Once again, Thank you, Ananda. Thank you, especially the organizer, coordinator, and Professor Ramar sir, please. Thank you, Professor.
Thank you, sir. Thank you so much.
Thanks a lot, Professor. Thanks a lot.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.